So today I want to talk about learning from human feedback and specifically reinforcement learning from human feedback. And so I'm going to talk about both, learning algorithms and how we get feedback and how we learn from it. So up until this point, most of the stuff we talked about was maximum likelihood training. And specifically, maximum likelihood training, we have some sort of input. This could be something like a prompt. We have an output, which is, our predicted output, and we calculate the log probability or negative log probability of the output given the input. And we want to basically minimize this negative log probability, minimize our loss. And so everybody knows about this. You're implementing a lot of the loss calculations and stuff is part of assignment 1. But there's a few problems with this. And here are some examples of problems with these learning algorithms. So problem number 1 is that some outputs or some mistakes are worse than others. And in the end, we want good outputs from our system. So some mistaken predictions hurt more than others, and we'd like to penalize them. So if I have the output be, please send this package to Pittsburgh, like let's say I have a machine translation system or a speech recognition system or something like that. And this is an output that I would like. If I make a mistake and turn this into please send a package to Pittsburgh, then that is, not a problem at all. I'll still get my intent across. But if it says, please send this package to Tokyo, then that would be a problem because my package might end up 13 time zones away. So, other things as like systems are being used in more consequential, decisions in our lives, there are things like maybe they're being used to make hiring decisions or help doctors diagnose diseases or something like this. And obviously, like if you diagnose a disease incorrectly, that's a much bigger problem than, giving somebody advice about where to eat like this weekend or something. So there's all kinds of differences in like the difference in both like the benefit and, harm that could be caused by different outputs. Also, you don't necessarily want your dialogue system to be swearing at your users or things like this. So there's also, politeness considerations, other things like that, stylistic considerations. So, if you mess up the syntax a little bit, it might not be a big issue. Messing up the semantics or style could be a much bigger issue. Another issue actually is that the gold standard that we have in maximum likelihood estimation isn't necessarily a gold standard. So corpora are full of outputs that we want a language model producing. And these can be wrong for a number of reasons. For example, Reddit or social networks are a great source of data for learning these models because they give us kind of like raw speech, the way that people, actually produce it. They give dialogue context, they give other things like this, but, there's a lot of bad content there that you wouldn't want ChatGPT spitting out at you. Disinformation is another example. Another surprisingly big problem, which is getting worse and worse, is a lot of the text on the internet is now machine generated. And like if you're training a machine translation system, for some low resource languages, the majority of the text online is from Google Translate from like 2007 or something like that. And Google Translate was really bad in 2007. So you don't want to be training your 2024 translation system on 2000 Google Translate text. So that's another problem. A final issue is something called exposure bias, which is more having to do with kind of like the search process or the actual generation process. And the problem is, let's say we could assume that all of our outputs were gold standard outputs, like we don't have any, just bad, poorly formed text or anything like that. What that means is when you have a prefix, the prefix is guaranteed to be good in your training data because all of your training data is good. But in reality, when you are generating text, you might not have good prefixes. So like your model might become a little bit confused. It might output some things that don't make a whole lot of sense. And then once you do that, now your prefix is no longer good. So at training time, you've only seen good prefixes. At test time, you don't see at test time, you don't see only good prefixes. So it kind of gets out of its element and it's not able to predict well. And this was called exposure bias. And one really common effect of this is repeating things over and over again. The reason why this happens is, and this still happens in models, it happens a lot less in models that have been, fine-tuned or RLHF for this, because they're able to solve these problems. But the reason why is like in good text, if a word is repeated over and over again, it's actually a good sign that that word should be repeated over and over again. Because language has this burstiness property where if you say a noun 5 times in a document, you're much more likely to say it again later in the document because that's like the topic of the document. So it makes a lot of sense. But on the other hand, language models tend to get in this like bad loop of repeating things over and over again. So that's largely an exposure bias problem. And there's other problems like that too. Any questions so far? Okay. Cool. So we'll be wanting to do reinforcement learning. And I'll define reinforcement learning later, but reinforcement learning, one of the most important ideas of it is a reward model or a reward function. And a reward is basically like measuring how good an output is. So the first thing we need to know is how do we measure how good outputs are? So there's a bunch of different ways to do this. We can measure it, the outputs objectively. This can be done, I'll explain all of these in a second. So we can do this objectively. We can do human subjective annotation or machine prediction of human preferences in some way. And then finally, there's something called extrinsic evaluation, where we use the output in another system and then measure the accuracy of that other system. So objective assessment is when we have an annotated correct answer, and we match against this. There are some cases where there is objective truth about the outputs. One example is solving math problems. Another is answering objective questions that really don't have, any argument about what the correct answer is, like where is the main campus of CMU located? Where is the main campus of Carnegie Mellon University located? Because if I say CMU, there's also Central Michigan University and other places like that. So Carnegie Mellon University. A very common example of this is solving math problems. And the most famous data set for solving math problems is something called GSM-8K. And in this, we have Beth bakes 24 batches of cookies in a week. If these cookies are shared amongst 16 people equally, how many cookies does each person consume? And so you can calculate this, and the answer is 3. But and the answer is 3. The answer could be written as like a number 3. It could be written as the word 3. It could be written as the answer is 3. But we'll assume that you can extract the answer and get the output in some way. The second thing that we can do is human evaluation. In human evaluation, basically, we have a source, we have a couple hypotheses about what the output may be, and we feed them to a human annotator, and that human annotator will give you a score. The score could be like correct or incorrect, or it could be a scalar score like 0.8 or 0.5 or something like this. So there's a number of ways we could do this. The human could also say A is better than B. So it could be like a pairwise assessment of this. First, talking about the direct assessment, we would give a score of like 2 out of 10 to send this package to Tokyo. And often we assign scores based on desirable traits. So for example, fluency, how fluent is the output? In translation, machine translation, another example is something like adequacy. How well does output reflect the semantics of the input? Factuality. So factuality is a little bit tricky, but for something like summarization, you can check whether everything in the output is entailed by the stuff in the input, whether everything in the output definitely holds given the what was said in the input. Other things like coherence, does the output fit coherently in a discourse, et cetera, et cetera. Some other things that people measure recently that actually I probably should have on my slides are, there's also, from the point of view of language model alignment, people often talk about helpfulness and harmlessness. These are kind of like fluency, adequacy, factuality, and coherence, but they're more vague, I guess. So like, how helpful is this output? Is this output potentially harmful in some way? Those would be other things that you could. When you have direct assessment, this is actually really hard. It's really hard to get good human agreement on direct assessment. So there's a few tricks that we do in order to get good human agreement on direct assessment. The first one is to come up with a rubric. So we say 5 on fluency means something completely natural, like a native speaker of the language wrote it. 4 says minor syntactic errors, syntactic or semantic errors that are slightly unnatural but don't affect, you know, the understanding of the sentence or something like that. And then you have those for like 1, 2, 3, 4, 5. Yeah.
So with human feedback, especially for stuff like fluency or adequacy, like wouldn't it be by nature somewhat subjective and biased specific to the person? So in practice, how do we make sure that the human feedback is introduced bias back into the model, or do we like average across the multiple?
Yeah. So how do we make sure this isn't, the question was, how do we make sure that this isn't biased? Because it's kind of inherently subjective. Very good question. I'm about to get to the second part of the question right now, which is, even after you do that, there's still some variance. Like some people are very picky, some people are not very picky. Like right now we're doing an exercise where we're doing some translation of like English to another language in my lab. And some of the people who are checking the translations are like, oh, this is wrong, this is wrong, this is wrong, this is wrong. And some of the other people are like, just looks good to me. So like there's also this sort of preference. And this actually can show up across languages. So like, for example, Japanese people are famously picky about whether like the output is good or not. And people from Spain, Spanish-speaking countries are famously like not picky. So once you've done that, another thing that people often do is they normalize by annotator. So they say like, okay, this annotator, we'll take all the scores given by the annotator and we will normalize them so that the mean is 0 and the variance is 1. And if you do that, then that makes sure that like you adjust for how strict that annotator is and other stuff like that. So that's another thing that people often. Yeah. Yep, I'm going to talk about that in a second too. Yeah. Great question. So the other thing that we can do is we can get preference rankings to get human feedback. And basically here we have, please send this package to Tokyo, please send a package to Pittsburgh. And here we would ask a human whether one is worse or one is better. This has a really big advantage that this can be easier and more intuitive to collect than direct assessment. It's also possible to get higher human agreement on this in general. One difficulty with this is it's hard to tell if the systems are really good or really bad. So like, let's say you did pairwise rankings for translation from English into Spanish, and then you also had pairwise rankings for translation from English into Burmese. And the Burmese systems would be way worse just because there's not a lot of training data. It's a harder translation pair and things like that. But nonetheless, you wouldn't be able to tell because you would just be saying which system is better. And you wouldn't like easily know whether it's a system that you could ship or not. So another problem with ranking is you can't like get a pairwise ranking of more than like 3 or 4 systems without like humans getting really overwhelmed and taking forever to do any rankings. So one common practice here is to do pairwise rankings And after you've done the pairwise rankings, you use an algorithm that turns pairwise rankings into overall scores. And there's a couple algorithms to do that, ELO and TrueSkill. These were traditionally used for like sports or video games or chess or other competitive things like that, where you have people play each other a lot and then get an overall score. And a thing that probably a lot of people know about, but maybe not everybody in the class, is oops, the chatbot arena. And the chatbot arena is it's basically a thing where you go in and if you go to battle, you can put in a prompt and say, please explain which language model is the best for summarization in the year 2024. And it will give you two answers. And they don't know the answer for like year 2024. So I guess what I could say is both are bad. But like if I say both are bad, and then there's a bunch of people who fill this out, and based on this, they go in and they calculate this arena score, which is an ELO score, normalizing the two, and you can see which ones are the best ones. And actually, as of I think yesterday or so, they put the new OpenAI models on the chatbot arena, and they're quite good. So you can go in and play with them here and rate them and give thumbs up or thumbs down. One thing, yeah. So anyway, that's a very common way to create rankings nowadays. Cool. Any questions about this? Yeah. The ELO score, so I don't know about ELO, actually, to be honest. I haven't looked at it super carefully. Maybe somebody else knows, but like the TrueSkill score has to do with like if you are a good if you have a TrueSkill score that's over this amount, we expect you to be winning this percentage of the time. Like the TrueSkill score differences, it has to do with like the statistical significance between them. I think ELO is pretty similar. Has anyone calculated ELO?
ELO is pretty similar. You can take the delta between two people's ELO score and calculate the probability that the person with the higher score would beat the person with the lower score.
Yeah, so I think that's basically what it is. It's kind of like a standard deviation style thing. Cool. Any other things? Okay, nice. Yeah, actually, one thing I should point out about the chatbot arena, this is a very amazing thing, very good service to the community. They also have a bunch of other statistics, like what percentage of the time one model beats the other one. So even if the ELO score is much higher, usually still the win rate is like 60 to 70% or something for the top models. And then they also have breakdowns by category. So if you want to find which one is better at like coding, for example, you click on the coding one and you get a ranking specifically for coding, or you want to find which one is good at Russian. And now we have a ranking specifically like for Russian models. So this is a great site. Cool. A few caveats about that are, I might get into this a little bit later, but when we talk about human preferences, different types of humans have different types of preferences, right? And so who do you think is using the chatbot arena to rank language models? Any ideas? Mostly language model researchers and like OSS language modeling people, you know, engineers, things like this. So it doesn't necessarily reflect it being good at, all the other things. Like I imagine there aren't a whole lot of Taylor Swift questions on the chatbot arena, despite that being all my daughter cares about. So like, you need to take these ratings with a grain of salt, but nonetheless, they're pretty good indicators of how good a model is. Cool. Another way you can get human feedback is error annotation. And this is annotating individual errors within the outputs. This looks like something like this. And again, a lot of my examples are from translation because I do a lot of work in translation, but translation also has a very long history of this sort of human evaluation, so it has strong established practices. And one example of this is there's actually a standard, I believe an ISO, International Standards Organization standard for how you annotate these translation outputs called multidimensional quality metrics. And basically what you do is you select spans that are errors in translation outputs, and you label how bad the error is and what type of error it is. So this would be like a minor linguistics conventions error because this would have been the appropriate thing to write here. This is a major accuracy error because it's Tokyo instead of Pittsburgh. So it would be like this. So the plus side for this is it gives more fine-grained feedback. It also can be more consistent because you're asking people to do a very concrete thing, but it can be very time-consuming, obviously. So these are some varieties of human evaluation. There's also automatic evaluation. In automatic evaluation, it's also called a bunch of other things. One popular way to call it is using LLMs as a judge. And the way it works is you basically feed it into a model, and the model or system, and the model or system gives you output, indicating how good the system output is. So the most common way to do it is through machine prediction of human preferences. And so if you have some sort of human annotations, you would predict it automatically using a model, automatic evaluation, reward models. And sometimes this uses a reference output. So for example, if you're evaluating translations, reference-based evaluation would use a human translation as a reference. Reference-free evaluation would use no human translation as a reference and just try to evaluate the input and output. So there's a bunch of different ways to do these types of evaluations. I'm just going to go through a few representative examples of them. But the first one is embedding-based evaluation. And embedding-based evaluation, the way it works is you do unsupervised calculation based on embedding similarity. And this is usually used together with reference-based evaluation because you want to calculate the similarity between a human reference or a correct answer and the output of the model. The most famous example of this is something called BERT score. And the way it works is, oh, sorry, this is very small, but we have a reference output, like the weather is cold today. We have a candidate output, it is freezing today. And we feed it through an embedding model. And from the embedding model, we get embeddings for each of the tokens. We then do pairwise cosine similarity between the embeddings for each of the tokens. In a way, this is like a lot like attention, right? We calculated the cosine similarity between embeddings for attention as well. And we get a matrix like this. And the matrix is basically the pairwise similarity between each of the tokens. And based on this matrix, we can calculate something like precision and recall. People are familiar with precision and recall from machine learning. Precision is basically how accurate is the stuff you output, and recall is how much do you recall all of the things that you're supposed to output. So the way this works is given this matrix, you take the maximum value in each row, and the maximum value in each row kind of indicates recall, because this is each row is a token in the reference, and you want to make sure that you have something that's close to each token in the reference. So if you have something that's close to each token in the reference, then you've covered everything in the reference. Otherwise, you have not, and you might be missing something important. You can also take the max in each column, and that indicates precision because that's making sure that everything that you output has some corresponding token in the reference. Then this is optional, but preferred. You multiply by IDF weights. I actually haven't talked about TF-IDF yet, right? Maybe no. So IDF weights are basically the inverse. Let's see. It's the inverse frequency of how frequently that appears in documents. So it is I shouldn't do this from memory, but it's like n, then it's minus, right? Is that correct? Somebody can somebody correct me?
It's n token given the data.
Negative log of the probability of the token.
It's log 1 over.
Oh yeah, it's
n
n
over
n over number of documents, right?
Yeah.
Yeah. Okay, got it. Thanks. So here n is the number of times this appears in the in a corpus, or the number of documents this appears in a corpus, and d is the number of documents overall in the corpus. So this will be higher for rare words, basically. And because it's higher for rare words get upweighted and they become more important in the calculations. So this is good basically because rare words tend to be more semantically meaningful, semantically important. Like whether, cold, and today are more important than is and the here. And so that upweights the rare words. And so after we do this, we do a normalized average of these cosine similarities and we get an output here. So this is a completely unsupervised metric. All you need to have is good embeddings for the likelihood of each of the tokens. Sorry, are there any questions here? Yeah. Yeah, so you could measure sentence embeddings. I think in general, sentence embeddings are worse than calculating the similarity between word embeddings for just about any reason, like worse accuracy for just about any application of this. So like, for example, even in retrieval models, you can do much better by looking on the word level than you can on the sentence level. The reason why we do use sentence embeddings is they can be very efficient when you're processing very large corpora. But like if you want the maximum accuracy, this sort of matching is usually better. And the reason why they're worse is just because you're trying to compress all of the information from the sentence in a single embedding, which is kind of hard. It's also the motivation for why we use attention. So, yeah.
We have the reference, so why is this unsupervised? Like we have a reference to compare.
Oh, so this is reference-based, but it's unsupervised. And what I mean by unsupervised, I'll explain in the next slide when I talk about a supervised method. Great question, though. So the next one is regression-based evaluation. In regression-based evaluation, basically what it's trying to do is it's trying to actually predict the value that the humans give. And so if we have a human assessment of how good the output is, like we have an assessment of its value being 0.5, then we have a model. This model is called Comet, which is why I use the Comet here. But we have a model that predicts it. And this made a mistake. And so what we do is we calculate the distance between these and we backprop into the model to update the model. So the reason why this is supervised is because we need human annotations of how good the output is in order to train this model, but unsupervised ones do not need any sort of annotation like that. Cool. So another paradigm is question answering based evaluation, or language models as a judge. And basically what you do is you ask a language model how good the output is. And this has been around for a while now. and overall, there are two paradigms. One paradigm is pairwise ranking. So you basically ask the language model exactly the same, question that you would ask, exactly the same question that you would ask a human when they were doing pairwise ranking, like which one of these two responses is better. For direct assessment, you would ask exactly the same question you would ask during direct assessment. So you would ask, how good is this on a score of 1 to 5? And so you just ask the language model the same thing. This is a nice method because it allows you to do a variety of things. It allows you to ask, either of these two varieties of questions. It also asks you it also allows you to ask very particular questions, like, does the response accurately use specific industry terminology and jargon or other things like this? And this, as a reference, you can look at Prometheus 2, which is a model that was trained specifically to do this, do both of these assessments. The problem with this is, the problem with evaluation, though, is evaluation can be inaccurate. It can make mistakes. And the way we tell how good a model is at being a judge is we do something we call meta evaluation. So evaluation of evaluation. And so we prepare a whole bunch of human ratings, and then we have the automatic ratings, and then we calculate some variety of correlation coefficient or absolute error of the predictions here. There's a lot of data sets that you can use to measure these sorts of things. I listed two here. The Conference on Machine Translation Shared Tasks are good for machine translation evaluation. SumEval is good for summarization evaluation. There's also a bunch of other ones more recently for kind of general language model evaluation as well. One thing to be aware of is language models can be very good at this. Like the state of the art on most of these things is asking a strong language model to do the assessment. But one problem is language models tend to be bad at the same things that they're bad at generating. So like detecting bugs in large code bases is not something, like language models are not good at generating bug-free code for large code bases. They're also not good at judging whether there's a bug in a large code base as well. And so the evaluation models tend to fail in the same places that the actual models tend to fail in generating things. So there's kind of a chicken and egg problem here, but that doesn't mean we shouldn't use them. Like language models are still our best tool to do this. So we can use them. Cool. Any questions here? Yeah.
Is it more common for them to have, like, for example, they mess up the variable names, or is it like a structural bug?
Oh, for bugs. Specifically talking about bugs, is it more common for them to mess up like variable names, structure, or semantics? I think it's common to do all of them, but the most common ones right now are like the syntax is correct, but it just didn't match the requirements of what should be implemented. Another thing is recently there's a lot of focus on code generation in like large code bases, and it doesn't fit well in the large code base. Like it looks locally coherent, but it doesn't work well with other stuff. Yeah. So yeah, we'll talk about code generation later too. Yeah.
So if human evaluation is still sort of gold standard whenever if you do have the resources and whenever you're testing a new system, is the subjectivity like coming out of just sort of how humans are like, is it more of a design issue in how you're providing the evaluation framework to humans? Or?
Yeah, this is a great question. So the question was basically, is the subjectivity or like the difference between human ratings based on like the instructions you're giving them, or where does it come from? I think there's a lot of places where this comes from, but depending on the difficulty of the task, sometimes it can be really difficult to evaluate. Like I cannot evaluate whether a language model gave a good answer to like medicine queries, for example, because it will know the right, like more or less the right terminology, even when it's completely off. Like one thing is I was recently looking at answers to a kind of like scientific question answering system, and it's completely wrong in some of the answers it gives about NLP questions, but I would be very surprised if like even most of the people in this room would be able to tell that, because it requires like specialized, knowledge about like what is the state of the art in this field, and unless you're working in that field, you wouldn't know the answer to that. So a lot of it comes from the competency of the annotators to be able to do a good job at the task. Another thing is, even if the annotators are competent, if they don't care about it, they're not going to do a good job. So let's say you're paying translators $5 an hour to assess, assess text, or even worse, you're paying them like $20 a sentence to assess text. They'll try to do it as fast as possible to get as many of those 20-cent bonuses and not try to do a good job unless they're incentivized to do a good job in some ways. So I think, competence, interest are really big ones. If you have competence and interest, then I think a big issue is how like carefully you can specify the annotation directions. So even for very competent, very interested people, doing assessment of like full paragraphs, for example, is really tough. It's like, do I give this a 6 or do I give this an 8? Unless you have a really careful criterion, it's hard to do that. So yeah.
So just to follow up on that, so when we're evaluating automatic metrics using human evaluators, doesn't that become a bit of an issue because it's subjective at the source of the evaluation?
Yeah, so does it become an issue? Does this subjectivity become an issue? And yes, it does, but usually what you do is you try to match the correlations with humans. So humans will very rarely have a correlation more than like 0.8 on something like this. Sometimes it's as low as 0.6. But usually our best models are even lower than that. So that's what you do. Great. Okay, so the next thing I want to talk about is extrinsic evaluation. So there's extrinsic evaluation and intrinsic evaluation. Extrinsic evaluation is basically evaluating the output quality by its utility downstream. And there are some examples like this, evaluating LLM summaries through QA accuracy. So you have a QA system, try to answer questions given a summary, and you see whether it can do a good job of that. Some other interesting ones are you translate and then see if you can answer questions based on the translated output. So this can be useful if you have a good extrinsic metric that's easier to measure than the intrinsic metric that you would be measuring over the text. Okay, so I've been talking about evaluation. Now I want to switch gears into like actually training models to maximize these evaluation metrics. And first, I'd like to define a few concepts. And the first concept is error. So error, basically, the way we measure this, specifically from the point of view of some variety of text generation, is we generate an output and we calculate its badness. The badness of the output is, for example, 1 minus an evaluation score. So if we have a blue score, or if we have Comet score or BERT score or something like that, the badness could be 1 minus the evaluation. In this, we will call the error. Generally, we want to be minimizing our error because, we're good. Like, let's assume that we're showing just one output to a human. We would like to be showing the best output to them on average. There's other things we could be maximizing. Like, let's say we're not showing one output to humans, but actually showing them 20 outputs, like in a search engine. Then we would want to be using a different metric that, considered the goodness of the 20 outputs that we're actually showing to humans. But for now, let's assume we're just showing them one. The problem with this, though, is we're using an argmax here. And argmax here is not a differentiable operation, or at the very least, it's piecewise constant, which means you don't get any gradient information when you take an argmax. So we can't use like backprop to optimize through this argmax function. And so let's look at methods that allow us to optimize despite this fact. So the first one, the first concept we can introduce here is something called risk. And risk is the expected error over all of the outputs. So let's say we have an input X, an output Y, and we have some sort of, let's assume we have a reference. The risk is basically we sum over all of the possible outputs, and we take the probability of the output according to the model, and we have the error. So this is the expected error under the model. So notably, this now includes the probability directly in the objective function. There's no non-differentiable operations included in this. So this means now that we have a differentiable function that we can optimize. But the problem is the sum is intractable because, like, as we talked about in structured prediction problems, the space of all of the outputs is exponential or infinite. So we couldn't take the sum over all of them. We'd run out of memory on our computer and time in the universe. So we would like to do something else to try to solve this problem. This is not super common, but it's maybe a little bit more straightforward to understand than the reinforcement learning algorithm. So I'll talk about minimum risk training first. And this is a method that allows you to directly minimize the risk. So the first thing that we do as part of this optimization is sampling for tractability. So normally what we would do in this case would be we create a sample of sentences anywhere between something like 5 and 50, and we calculate the risk over this sample. And so here we have a sample, and we calculate the probability. We renormalize by z, where z is a normalizing constant equivalent to the sum of all of the probabilities that we get here. And then we can calculate the error here. So this is an approximation of what we actually want to calculate. So we actually would want to calculate this risk. But instead, we're subsampling a smaller set and renormalizing so that everything adds up to 1. These samples can be created using sampling or n-best search. And if we're sampling, we want to make sure that we don't have any duplicate samples here. So we would be sampling without replacement and be getting unique samples according to a sampling algorithm. So there's advantages and disadvantages of sampling. Sampling will give you a more diverse set of things to optimize over, but if you get the top n outputs, then you would be getting the best ones. So there's kind of a trade-off here. Are there any questions here? Yeah.
Wouldn't we want the samples with the most probability too, because they would be...
Wouldn't we want the samples with the most probability? So it's a good question, which one we would want. Like in reality, we want everything. We would like to optimize over everything, but we can't. If we sample, and this is a common problem. This is also a problem in retrieval. It's a problem in a lot of other places. And we're faced with a trade-off of getting, like, let's say, we have a probability or a log probability where the log probability of the most top likely sequence is like -4. Then we have -6, -8, -10. And so we have a few samples that have relatively high probability, more that have low, many more that have lower, many more that have lower. And so basically our hypotheses look like this with respect to log probability. If we take all of the top ones, we will get ones that are likely, and we will be able to distinguish between them. The problem is the top ones might all be good, for instance. So they might all be like perfectly fine outputs. And so we won't get very many negative examples. And so we might, like, let's say all of them had an error that was close to 0, we just lose our learning signal. However, if we had ones up here that had very high error, then yes, definitely we'd want to be penalizing them. And if we took random ones down here, maybe they're all so bad that like we shouldn't even be considering them. And so this is, this is a common problem. Like if we're trying to somehow slightly raise the probability of a high score of like the highest scoring one versus other very good ones, then actually that can distort the model and cause the model to, get worse overall. So, yeah.
Can this prefer shorter sequences over longer ones? Because longer sequences will always have lesser probability.
Doesn't this prefer shorter sequences over longer ones because the longer ones will have lesser probability? That's a great question, but actually the answer to that is no. And the reason why is because this is what we are optimizing. And we're trying to optimize this to lower the risk. And to lower the risk, that means we will upweight probabilities that have low error, regardless of whether they're long or short. And normal maximum likelihood actually kind of prefers shorter sequences because it's just maximizing the likelihood, but this actually can fix the problems with respect to length to some extent. And if you look at a base model versus an RLHF model, for example, the base models are very short in their responses because they were trained mostly with maximum likelihood. And then if you look at ChatGPT, it will chat at you for, 5,000 tokens, right? Because the humans tend to prefer longer outputs when they read outputs. Like if you give people a long output and a short output that say the same thing, they look at the long output and they're like, oh, the language model is really trying, It makes you feel like the language model cares about its job and is doing things. So people tend to give those thumbs up more often. And so this can actually correct for length problems, length issues. Yeah. Great question though. Cool. So this is very straightforward. I think it's, I think most people if you've taken a machine learning class, or a math class, what an expectation is. We want to minimize the expectation so that on average, if we sample from our model, we get the lowest error. And this is how we can do it. We can just kind of optimize this function and we'll get the lowest expected error if we create the model that way. However, there are some problems with this. One big problem, and one reason why people don't use this method very often, is you still need to sample multiple or many outputs for each input you have because you need to compare against them in the sum. And because of this, it's actually quite a bit more frequent, quite a bit more common nowadays to use reinforcement learning methods that actually allow you to step away from this a little bit. So reinforcement learning basics. The first reinforcement learning method I want to talk about is something called policy gradient. But before I do that, let's talk about reinforcement learning. So reinforcement learning is a learning setting where we have an environment. We have the ability to take actions in the environment, and we get a delayed reward. If you look at the recommended reading for this class, there's an example of Pong. And in Pong, the game, you have an observed image, X. You have an action of moving up or down. And R is whether you win or lose at the end of a game. So this is a very simple action space. If we're talking about training a language model, what do you think is the environment? What actions can you take? And what delayed reward would you be able to get? And this could be various depending on the type of like natural language processing task you're trying to handle. But any examples? Any ideas? Playing chess with a language model? I mean, you can play chess with a language model. Like, let's say you were playing chess with a language model. What would your environment look like? Might be a textual representation of a chessboard or something like that. And then the ability to take actions would be being able to output a chess move or something. Yeah. It could be a chain of thought. It could be the ability to output tokens in a chain of thought that end with a chess move also. So that would be another way. Yeah.
You rewarded based on the rhyming scheme. If it's A, B, B, you give it more rewards. If it's not following the rhyming scheme, you give it a lesser reward.
Okay, yeah, so that's great. So for poem generation, our reward model, you could give it a higher reward if it rhymes, and a lower reward if it doesn't rhyme. Do you have an idea of what the environment might look like? You might have a human giving it like something to write a poem about, right? Like I want to write a poem about like about differential equations, like Elon Musk, like Elon Musk was explaining them or something like that. You know, that could be your environment. And then usually in language models, the ability to take actions is picking from the vocabulary. So each action is a choice from the vocabulary or something. So these are just some examples. You can, you know, put them onto whatever task you care about. In ChatGPT, your environment, the environment is like somebody is chatting with you on ChatGPT, and your reward would be that you output responses that are helpful and not harmful, basically. But anyway, yeah. There's several reasons why you might want to do reinforcement learning in NLP, and they're actually a little bit different. You might have a typical reinforcement learning scenario like dialogue, like ChatGPT, where you can make responses and get a reward at the end. Actually, ChatGPT is not even as good as an example as like a flight booking system on the phone. Because a flight booking system on the phone, like you have a very clear reward, which is whether you successfully booked a flight or not. ChatGPT, people might give thumbs up and thumbs down, but most of the time they don't. So it's a little bit trickier. Other times when you might want to do reinforcement learning are when you have latent variables. What do I mean by latent variables? Chains of thought could be an example of a latent variable. So last class, I talked about process reward, which was where we have a chain of thought and we had some like choices of, you know, like this part of the chain of thought was good, this part of the chain of thought was bad. We had like a green and red plot. That's an example where we have a math question, we have the answer to the math question, but we don't know what the chain of thought in the middle should be. And so that's an example of where we would want to be optimizing a latent variable and finding the latent variable. So you do rollouts where we generate latent variables, grade them, and then upweight the ones that are good, downweight the ones that are bad. Other examples are when we have a sequence level evaluation metric that we can't optimize without first generating the whole sequence. So this could be any of the like automatic evaluation metrics that I talked about before. So we might even know the correct answer. We might even know like a good translation, but we want to optimize an evaluation metric that we talked about instead. So again, I'll go back to supervised maximum likelihood. This is where we have, you know, an input and an output, and we want to optimize the likelihood of the output. In the context of reinforcement learning, this is also called imitation learning. And imitation learning is any variety of thing where we're like imitating a teacher, and we want to take the same actions that the teacher took, or we want to somehow like learn from the actions that our teacher gave us. In this case, the teacher's actions would be the gold standard output. Maximum likelihood is one variety of of imitation learning, but there are also other varieties of imitation learning where like every time you get off the path, off the gold standard path, it tries to push you back onto the gold standard path and other stuff like that. Another variety of learning is called self-training. And self-training is where we sample or argmax according to the current model. So we either sample the output or we get the maximum likelihood output using something like greedy search. And then we use the sample or samples to maximize likelihood. So the self-training objective here, instead of having the gold standard output, we have the output that was sampled by the model. So here, one interesting thing about this is we don't need any gold standard outputs. We just need the inputs. But does this seem like a good idea? I see people shaking their heads. Why not?
Because if the answer is wrong, it will keep rewarding the wrong answer.
Yeah, if the answer is wrong, it will keep rewarding the wrong answers. So it will, if the model is making mistakes, it will just reinforce the mistakes that the model is already making, right? That being said, it can still work. So some examples of when it can work is if we specifically use the argmax here, and this argmax is, or the highest likelihood output is more likely to be correct than not. You can improve the accuracy by training on this to some extent. There's also other successful attempts. So there are methods called, there's a method called code training, where we only use outputs where multiple models agree on them. So we generate an output from two models, maybe weaker models, and we find the ones where both of the models agree on the output or have high agreement scores or something like that, and use only those to do self-training, and that can help significantly. Another successful alternative is adding noise to the input to match the fact that we have noise in the output, and that can make has been found to make models more robust. Also, recently, there have been some works on kind of on self-training with large language models. And a lot of these, what they do is they generate a large corpus of output, and then they do some sort of filtering of consistency of the whole corpus. So they only use a single model, but they find the outputs that look like all of the other outputs and filter out the ones that don't. I don't have them on the slides, but I'd be happy to share them if that sounds interesting later. Okay. But anyway, self-training, I mostly introduced it as a intermediate step to reinforcement learning. And here, what we do in reinforcement learning is we add a term that scales the loss by the reward. So instead of just measuring the output of the model-generated loss, we also multiply it by a reward. And this reward can be, an evaluation metric that we calculate automatically. And outputs that get, what this means is outputs that get a bigger reward will get a higher weight according to the model. If we think about this, under certain conditions, this is equal to or very similar to maximum likelihood estimation. Does anybody have an idea about what condition that would be under? If you think about both of the equations. If R is equal to 1, in some cases and equal to 0 in other cases. But what case does it need to be equal to 1?
R is like an indicator that y is equal to y hat.
Yep, exactly. If R is an indicator that y is equal to y hat. So basically, if we're talking about exact match between the outputs, and you get a reward of 1 when the generated output is exactly equal to the kind of reference output and a reward of 0 otherwise, then this will essentially be equal to maximum likelihood. So, but, you know, this is broader than maximum likelihood. We can give soft rewards to say things that are, you know, close to the reference are get a higher score. So this is good. And this is guaranteed to essentially minimize the risk. So this is another method for minimizing the risk, similar to minimum risk training. The problem, though, is this can be very unstable. When can this be unstable? Number one, let's say you're starting from scratch with a completely untrained language model. No matter how many times you sample from it, it's not going to be able to solve complex math problems, right? So you'll sample and sample and sample and sample and sample, and you'll never get a reward that's more than 0. So you'll just spin your wheels forever and never learn anything. Another reason why it can be unstable is even in the case where you do get rewards, they can be pretty sparse. And so you'll be getting rewards semi-randomly. And you might have a good model that was trained using maximum likelihood, but your steps, like you'll be taking random steps that greatly increase the reward, and then you'll get no reward for a long time, and random steps that greatly increase the reward. And so this can be a problem and makes it very hard to learn. So there's a number of ways to fix this. One of the big problems is credit assignment. And I mentioned this briefly last time, but the problem with credit assignment is how do we know which action led to the rewards that we're getting? The best scenario for this is that we get an immediate reward every time we take an action. And so that would be, we get a reward on like every single token that we generate. So the first token, we get no reward. The second token, we get +1. The next token, we get +0. And these directly correspond to how good that token is. The worst scenario is that we only get it at the very end of a rollout. So this would be an example where a dialogue system that's trying to book an airline for you gets a reward after talking to you for 10 minutes. And you don't know exactly where it went off the rails. So often there's a practice, especially for very long sequences, of assigning decaying rewards for future events. And so this would be something like, let's say we have a very long conversation, you would assign more reward to the things at the very end of the conversation than you would for the things in the beginning of the conversation. There's also, actually, I think I'll talk about this later. Yeah, so maybe I'll talk about it on a later slide. So now let's talk about some methods for stabilizing reinforcement learning. So sampling can be a problem, as I mentioned before here. It's particularly unstable when you have very big output spaces, like words of a vocabulary. And a number of strategies can be used to stabilize reinforcement learning algorithms. The first one, which is like used all the time nowadays, we barely would even consider doing it without this, is pre-training your model to be as good as possible before you start doing reinforcement learning. And so you start training with MLE, you know, like we have a pre-trained base model, and then we switch over to RL before we do that. And in fact, nowadays, we don't just pre-train, we also do fine-tuning, like instruction tuning, before we switch over to RL. And that's also, we can start from the best place possible before getting into the hard, expensive, and unstable RL. So notably, this only works in scenarios where we can run MLE. So like if we wanted to generate, like, let's say we wanted to generate latent mathematical proofs or something like that, and we had a model that was not trained on any mathematical proof data. Obviously, we can't pre-train on MLE because we don't have any data for it, but in most cases, this should be possible. Another thing that goes into most reinforcement learning algorithms nowadays is regularization to an existing model. And what this means is we have an existing model and we want to prevent our model from moving too far away from the existing model. And the existing model might be our like best instruction tuned model. And the most typical way to do this is to introduce something called KL regularization. And KL regularization is basically where we have an old model and we have the new model. And we calculate the KL divergence between the old model and the new model. And we subtract it out from any reward that we get. And so our objective here is twofold. We want to keep the model similar. You'll notice I've added another thing here. And this is an objective that improves reward. So instead of just calculating the probability times the reward, we calculate the ratio of the probability of the reward according to the new model divided by the probability of the reward according to the old model. And so what this does is this measures the ratio of improvement of reward. And this is according to a method introduced by Schulman. And then this was shortly followed up by something called proximal policy optimization. And this has this ratio involved here. And the ratio is what I talked about up here. But then they also have a clipping term. And what the clipping term does is it basically prevents you from having large jumps away from the model. So both of them are kind of, you know, similar in nature. They have similar motivations. But in the PPO paper, people, they basically demonstrated that this clipping term was a more stable way of doing this. Recently, people have not been moving away from PPO and using the more simple KL regularization method. But I think basically both of them serve similar purposes, and you kind of need one of them in your model, in your training, regardless of which one you choose. So another thing that's rather common in models is adding a baseline. And the basic idea is we have expectations about how difficult a particular instance may be to solve. And so let's say we're handling a translation task, and our input is either this is an easy sentence or buffalo, buffalo, buffalo. If you don't know about buffalo, 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 you can search for buffalo, buffalo, buffalo on Wikipedia and see what I'm talking about. But it's a tricky English sentence where you say buffalo, 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 or something like that. And that's a well-formed English sentence. But anyway, like let's say we got a reward of 0.8 for translating the first sentence and a reward of 0.3 for translating the second sentence. The problem with this is based on our expectation, we would expect that we would almost always get this right? So this sentence we should get right. This sentence is really hard to get right. So we kind of expect to get it wrong. And so what a baseline gives us is it gives us our like a priori expectation of what the reward is going to be. And then our final reward when we you know, train the model is the difference between these two. So we have here we underperformed our expectation, so we actually penalize the output. And here we outperformed our expectation, so we improve the output. And so then we optimize with respect to this this reward, baseline reward minus baseline. One thing I should note is that as long as the baseline satisfies a few light kind of constraints and you don't backprop into the baseline, this will still allow you to optimize the reward. The only difference is that it can reduce the variance in the reward, so it can reduce the sparsity in the reward to some extent, and that will improve the stability of training. So this is a good tool to use. How do we calculate these baselines when we train models? It's basically arbitrary. So you can pick anything you want as long as you're not referring, for example, to as long as you're not backpropping into it or referring to the output here or other things like this. But one is you can predict the final reward using a linear layer from the current state. So this is what was originally introduced in this kind of classic paper on reinforcement learning. You can calculate the reward for entire instances, or you can calculate it for each decoder state, or the baseline, sorry. Another common thing to do is to use the mean of rewards in the batch, or the mean of recent rewards as the baseline. And so basically what this means is as your model is getting better and better, your reward will be like looking like this. Your reward will be going up. So you're using kind of the rolling average over one batch or over multiple batches is your baseline. And so if you're outperforming your recent performance, then you do better. If you're underperforming your recent performance, you do worse. Cool. Any questions about this? Yeah. Yes, so this is still used pretty frequently today. This is used a little bit less frequently. I think it's actually more effective, but more complex, so people don't use this as much. Another thing is if you're training using something like this sort of policy gradient or something like that, baselines are rather important. If you're using something like DPO, which I'm going to talk about in a second, it's not as necessary anymore. So I'll talk about that. Cool. So the final method I want to talk about is contrasting pairwise examples. So like one of the things I mentioned is one of the motivations for going from risk to not using risk was it kind of reduces the number of sentences that you need to process at any point. But actually recently, there's been kind of a move back towards contrasting pairwise examples. And the reason for this is you can learn directly from pairwise preferences, either human preferences or a model that was trained to mimic human preferences. And this can provide more stability, even if it is a little bit more computationally expensive because you need to process two outputs at once. And the most popular method for this is a DPO. And the way DPO works is basically it calculates the log of the sigmoid of the probability ratio of a winning output minus the probability ratio of a losing output. So you want to increase the probability ratio of the winning output, decrease the probability ratio of the losing output. And the sigmoid basically is saying if the difference between these is very high, if the difference between these is very high or very low, you're not going to be getting a very big gradient. But if you're right in the middle where like any changes you make a big difference between the winning and losing ones, the ratio of the winning and losing ones, and that gives you a bigger advantage. And this is the intuition behind why this is a good method, but there's a lot of derivations of how this matches kind of the overall objectives of reinforcement learning in the paper. Another really useful thing, which is useful for just about any objective, but it's particularly important when you're doing something unstable like reinforcement learning, is because each sample has high variance, you can sample many different examples before performing an update. And another thing that you can do is save previous rollouts and reuse them when you update the parameters. So this is just increasing batch size, right? So you're just increasing the number of examples. We talked about this already because we talked about the reason why having larger batches is useful just from the point of view of maximum likelihood also. It stabilizes the gradients. It makes sure you're moving in the direction that improves the model overall and not for a single instance. separately from that, experience replay is useful because in the process of reinforcement learning, you're modifying the model. And for example, you can modify the model to become worse, or you can modify the model to become better. And either way, it's useful to I erased the figure that I had before, but basically it's good to be contrasting like worse outputs and better outputs, regardless of those worse outputs are from the current model or the previous models, because if you only have good outputs, you might be comparing against just overall good outputs and be downweighting outputs that are also good. And that causes your model to actually get worse because you're penalizing good outputs. If you only have bad outputs from any model, then that's also a problem because you do want good outputs to be upweighting appropriately. So having a mix of good outputs and bad outputs can be useful, and experience replay helps with that.